please welcome Johannes Schaback.
Thank you very much, Johannes. All right, that's the clicker. Fantastic. So AI is, well, first of all, welcome at the early hour. I hope that you're all awake. It's a pleasure to be here. It's an honor, actually, as a matter of fact, because I met Sophie and Serge quite a while ago. And as you probably recall, I've been doing business angel investments all along. And so we've been in touch with Sophie for a very long time. So AI is, for me, it's very special and a super enthusiastic field because there's so much going on that, as a matter of fact, every week there's a pop-up of a new topic. And that's also why I took a little longer to prepare my speech today, because I thought, what am I going really to say? There is such an esteemed audience. Stuff that I talk about is deep learning. Right? So what you can do in deep learning, etc., but that would probably bore you because that's a private session and I wanted to do something special. So what I'm going to talk about is, not what will happen in the far future, the Terminator setup, everybody will be unemployed, etc., stuff like that, which is pretty much science fiction for me and in the realm of speculation. But I rather would look at what's going to happen with AI tomorrow. Where could the next step for intelligence come from? Right? And this is basically the theme of my talk for AI and tomorrow. So I've been a practitioner. I run a company called Visual Meta, which is 250 people. We're basically an AI company. We do machine learning for classifying products from Amazon, eBay, Zalando, etc., based on images and text. And one important note is that while I was at Shanghai Jiaotang University, I met a very, very smart person called Sebastian Novozin, who has been very, very active in the research on machine learning back then, particularly in computer vision, and who's now at Cambridge, basically at Microsoft Research in Cambridge, and who basically inspired me for many of the topics that I'm going to talk about in a moment. So let me get started right away. Where will the next big step and leap for artificial intelligence and maybe even artificial general intelligence come from? So obviously, composable differentiable architectures is the big thing, right? I mean, there is no doubt that in the field of deep learning, which is basically composable differentiable architectures, has been a great, great progress in recent years. This is fantastic because it's basically the system of building Lego blocks, having Lego blocks that are differentiable, that you can mix and match and compose together in order to build architectures that actually learn. And this democratizes and basically frees up increases the amount of freedom that you have in order to build learning systems and big systems. And that's fantastic. And one particular example that I picked here is the FragNet, which is basically a very deep neural network, about 159 or even more layers that are composed in a systematic manner. And the cool thing about that is that even though it's super, super deep, and you probably all know that because you're in the field of machine learning, that basically not, the deeper you make a neural network, the harder it gets to train, because you have to propagate up or back propagate an error and update all the weights. And so that's a little bit the issue with deep learning that has been solved basically by reducing the amount of edges or basically other tricks that have been introduced. So in this particular case, in FragNet, the cool thing is that the machine tries to, has hypotheses about particular path that it could go. Is there actually a pointer? No. That it could go through the different branches of the subnets and basically pick, based on the hypothesis, those that actually make sense most. And this is really cool because from what we gather, the brain has a similar tendency, has a similar strategy to work like that. So based on these patterns, these Lego blocks, there is now a huge variety of different patterns that you can employ. As a matter of fact, most of the research in deep learning is currently conducted in the meta sphere, as I would call it, right? How do you compose these building blocks? How do you learn to learn, right? By gradient descent, very popular paper. How do you basically infer from data? What's happening in the unsupervised learning space? And with all these possibilities and combinations, everybody can basically, it's very, very easy to compose different learning systems. So there's probably a big leap forward coming still from deep learning. One particular example that's been very, very hot in recent years is basically generative adversarial networks, where you would train two networks that compete against each other, where you would have a generator that generates fake, let's say images or samples, fake images that would be digested or try to be discriminated by a discriminator, deciding on whether this particular sample it sees is either a fake or a real one. So it would get fed by real samples or by the generator samples, which are fake. And then it would learn to distinguish between fake and not fake. And if it would discover, or it would basically classify correctly that a particular sample is fake, so then it would basically be feedback to the generator and helping the generator to improve its model on generating samples. So you could sample then out of, let's say, it could be a normal distribution, or it could be basically a Latin space area there. The cool thing is the machine learns in an unsupervised way the inherent structure of the data. And that's, I think, one of the current biggest topics, because humans, or as we could look at it in biology, we're also not having a god or like an overarching supervised teacher that tells us every time you did right or wrong, but as a matter of fact we learn continuously and in a way unsupervised. And basically understanding the inherent structure that the generator will then be able to learn, such as in these examples, you could even draw from the previously learned samples and create entirely new pictures or outputs. In this particular example, for example, if you look at the horses that are then basically drawn or redrawn as zebras. So this is very exciting, and there is far more of this to come. And as a matter of fact, it's a little scary as well, because if you think to apply that to faces, there's a lot of stuff you can do if you really further think down that road. So that's so far for composable differentiable architectures. There's far more in a field that is more coming from neuroscience, cognitive science, biology, and physics. As a matter of fact, I sometimes have the feeling that we as computer scientists are a little egocentric. We currently have a tendency, not all of us, but we sometimes have a tendency to think, okay, intelligence is probably something that will originate or stem from computer science alone. Rather, to look at, what are the different fields, the different disciplines doing. As a matter of fact, in neuroscience, there's been great progress in recent years. And so neglecting that would be just foolish, such that I would like to shed some light on that. So brain simulations in particular might be the safe road to intelligence, because it would just copy how the brain works, and from that we could infer and reverse engineer in the brain. The problem obviously is, how to measure that. The censoring, slicing it up is very difficult, but it would basically help us to understand first copy, even though we don't fully understand it, and then try to, dissect it better on. So, however, this is very difficult, as I said, because you basically, somehow need to get that data, right? And the problem is, if you stick probes into the brain, for example, or in some sort of tissue, you actually damage the tissue, and you influence the system that you actually want to measure by, probing it. So a little like Schrödinger's cat, if you will. So the problem is that multi-electrode arrays are super, super helpful for locally understanding what's going on in a neural network, in an organic neural network. But obviously, it's still a little crude. So there are other ways of basically looking at and trying to infer how the biological neural network works from optogenetics, which I find personally quite interesting, where you would inject a certain protein via a carrier virus or so into a cell, a neuron, where once it's been lit up by blue light, it would fire, right? And by that, if you pick the right neurons and you target the neurons right, you can actually activate certain behaviors within a mouse or within a biological neural network. And that's quite interesting, because from that, and if you think that further, is quite a lot of stuff happening in that field. Also, a field that's connectonomics is looking at the brain, or rather at neural networks, at a network as a huge graph. And what can you infer from graphs? right? There's been huge studies and research on what you can do on graphs and how to understand graphs that are massive. And this is basically this, research that basically tries to understand, is there inherent patterns in the connection, just in the pure connections that make sense, and from which we can better understand what intelligence means. So another field is algorithmic information theory, and a little bit the problem of missing the definition of what's intelligence as a matter of fact. At least I have the problem that there is a floating amount of definitions of what intelligence means. So if you look at deep learning, then you usually prove that your algorithm is smarter than somebody else is by proving that on ImageNet or other data sets, the accuracy, the precision and recall is better. Or the F1 score. It doesn't really matter how you measure, but it's basically always bound to the data set that you have. And there is no real common understanding that is that's funded or that's based on fundamental theory, basically on fundamental mathematics and laws that basically define what intelligence really is. There are a couple, but one particular one is the one brought forward by Marcus Hutter. And the thing is that if we are to talk about intelligence, we don't really know what we're talking about, and everybody has a different understanding. So the big idea was to say, okay, let's name it, let's agree on something, let's agree on a theory, and this is what we think is that are the properties that intelligence should reveal and show, and then let's go on forward, and it will target us and focus us much more towards building actual general intelligence. So basically, Marcus Hutter brought forward the universal artificial intelligence definition as basically a mix-up of, or basically a combination rather, of different, already existing theories. And as a matter of fact, it's pretty much a Turing machine that has a reinforcement or Bayesian reinforcement learning core in itself. So you would basically have a tape, as usually happens in Turing machines, that defines the environment. And the agent would learn based on that and would act according to its own decisions. It would censor the environment. It's very simple in a way, and would basically act according to it. Also, if the environment is actually computable, you would have a Turing machine that generates the environment, the world, as well. So the actual difference is here that, again, the IXC model is not particularly more powerful than current deep learning approaches, but it's based on a fundamental and consistent and coherent theory that basically provides a theoretical framework that defines, that is consistent within that framework for defining intelligence. And that's really, really interesting. So another topic is that we may not be able to create intelligence by design. We may not be able to write code or to train it in terms of deep learning that basically we could engineer it with deep learning or other machine learning algorithms. But as a matter of fact, intelligence may be actually coming out of evolution. So you can't generate intelligence without basically building an environment that's fruitful enough, that's big enough, that's simulating life in its complexity as it is without, and then basically, hopefully, praying that at some point artificial intelligence or the actual intelligence would evolve. Because at the moment, if you look at what we currently do, AI, as we all know, is very narrow, right? It lives in a laboratory. It's not exactly stipulated or stimulated very well. But as a matter of fact, if we were to build a world that is like the Matrix, from the movie, very, very consistent and physically accurate, and all the laws of physics and all the necessary preconditions that you would have for evolution would be met, then we could sit back and wait, run a couple genetic algorithms and wait. But obviously, the problem is that with genetic algorithm, we're particularly simulating life and then hoping that intelligence would evolve comes with the cost that it might never happen. As a matter of fact, so there is Sebastian Novotny, I mentioned earlier, he brought forward that the Fermi paradox tells us that basically life may be actually abundant. It might actually happen in in cosmology. It might be there, but intelligent life is super, super rare, right? As we know, because otherwise we would have noticed by now, or we would have been contacted by alien life, just statistically. So waiting for this to happen is quite annoying. Plus, it might be that we're not really building an intelligence that's actually useful. So this, what I just talked about is basically built up on an information theory that has been brought forward by a gentleman, a neuroscientist, Tononi, who's been basically saying that in order to define consciousness, we have to assume that there is a physical system that basically that comes with certain properties such that the consciousness can derive from that physical system. So that's basically the theory behind, simulating artificial life such that we can evolve a consciousness or a little bit beyond, basically first maybe an intelligence. So another topic that I find interesting is at the moment that, in the cognitive science space, that there is quite an upsteer by a theory that's called embodied cognition. So what embodied cognition's trying to say is that a consciousness is very, very much dependent on your body, right? So you can't be intelligent, you can't have a conscious without a body. And the way how we perceive ourselves and how we are conscious is very much dependent on the body. It might even be that the body is more influential to our consciousness than we think. And one way of thinking of that is now that we have all these wonderful autonomous systems that are super complex, that generate massive amount of data, that have all the capabilities in the world to act, to sense, to plan, and to act. We might actually get in a setting that embodied cognition could actually become feasible, or at least a setup where this could work. So this is, again, it's not speculation. It's there. It's been observed. It's in cognitive science, and this is basically the idea to have that we now in a setup that everything that we build, especially in the autonomous way, we could build a cognition part where, because the environment that it senses gets so complex and the body it becomes so powerful that this could work. So another one that, if you recall what I talked about previously, that if you're thinking about simulation, thinking about what could be, agents that sense, that could derive some sort of consciousness, I believe that, as we see with Pac-Man or Go earlier this year, the next step for intelligence is certainly to play more complex games. You would think, okay, game playing, that's ridiculous. It's, we do that for fun. But as a matter of fact, games address a certain region in our brain that, stimulates our intellect, right? I mean, there are many games of skill, or many games that require certain planning and certain behavior that are very, very basic. You could call it intelligent. So to progress down that road does make a lot of sense. So one particular, if you compare Pac-Man or even Go to the games that are already out there, right, which we think of simulations of the real world, then there are fantastic examples. Obviously, we have to ask ourselves, if we now become more proficient in playing Grand Theft Auto, what purpose does it serve? But it might help us to understand, what sort of intelligence, what sort of behavior does an agent and within that world actually reveal. So I very much look forward to the StarCraft challenge, because it's not a round or a turn-based game as is Go, but it's actually a real-time game where certain properties of intelligence, quick reaction, there are certain necessities that are very, very different from classical board games. So once this is done, and I believe that within the next year we'll have a StarCraft bot, or in the StarCraft AI, that will outperform human players. So that's it for gaming. The last and maybe most, economically important STEM are certainly knowledge bases. And I was wondering how I should put it there, because in the matter of fact, what I wanted to say is that we somehow, in the machine learning area, would need to bring together implicit and explicit knowledge. So trained knowledge that we could learn from neural networks, and explicit knowledge that's present in databases, right? That somebody wrote manually. And bringing that together would help us build incredibly strong or incredibly smart machines. As a matter of fact, Siri, Alexa, etc., they already work with knowledge graphs, right, which are basically discrete data structures, huge graphs where you would have different edges that define the relationship between data. And if you would need to answer a question in a certain realm, like chemistry or so, then you would basically traverse that graph, and while traversing the graph, try to reason your way through to the answer, right? And this is once you can formulate a query properly, you can get all the knowledge that's in the graph out there already, right? So that's fantastic, and there is huge knowledge graphs out there, but obviously there's not one that would encompass all the knowledge of the Wikipedia. So building up a knowledge graph by machine learning, super interesting, and harnessing and making use of knowledge graphs together with machine learning would be a fantastic accomplishment. So one particular paper is the end-to-end memory networks that tries to do that by basically using a key value store. And as a matter of fact, there's a lot of going on in what memory could we have in machine learning. So one particular example is end-to-end memory networks, where you would map basically word embeddings from different from the text in order to build up a question answering system. So there is progress towards that, and it's quite promising, and I'm very, very sure that within the next years we're going to see a lot more in that area. All right, so all in all, I think, as I said earlier, for us machine learners, it does make sense to look a little bit beyond our normal realm, even though it's super exciting what's happening in deep learning, and try to be open-minded what's happening in other disciplines, be it neuroscience, be it physics, be it psychology, be it cognitive sciences, etc. I guess there is so much to learn. There's been so much research invested that for us, we can definitely benefit on that, harvest that, and build smarter machines. So that's it. Thanks a lot.
Thank you. Thank you, Johannes.